Let's talk about, finally start chapter 2 on differential equations of higher order, second order, third order, fifth order, 97th order differential equations, you name it, all right? So those are differential equations where the order of the derivative, the highest order of the derivative that appears in it is other than the first derivative. However, we're not ready yet. We need some tools and some definitions before getting into the actual solving the equation. So we need what we call the superposition principle. Talk about linear dependence and linear independence. Let's also talk about the Wronskian and the criterion for linearly independent solutions. Okay, so this is this equation. We have a couple of equations here. A linear and order differential equation of the form blah blah blah. That is the n derivative plus one derivative less times some coefficient, but actually, remember, this differential equation is linear if none of the terms containing the y's or any of its derivatives are raised to a power other than 1 or are part of a function like a sine, like a cosine or something, and the coefficients are just functions of the independent variable only, or maybe just numerical values, all right? Well, we have a special definition here. Number one, this equation happens to be homogeneous if the right-hand side of the differential equation is 0. On the other hand, if the right-hand side is something other than 0, we have a non-homogeneous differential equation. Okay, let's not get into the methods of solutions for now. All right? Okay. Let's consider the following differential equation. Okay, consider the differential equation, the third order linear differential equation: y triple prime minus 2y double prime plus 9y prime minus 18y. Verify that each function a, b, a through d, d is on the right on the next page, is a solution to the differential equation, and we're going to talk about it. Okay, so we have y equals e to the x, y prime equals to e to the 2x, y double prime equals 4e to the 2x, and y triple prime equals 8e to the 2x. All right. So what do we do here? Well, let's check that it is a solution. How? By substituting everything into the differential equation. Well, so there's quite a lot to write right here. So that is, on the one hand, y triple prime, which is 8 e to the 2x, plus, or rather minus, 2 times y double prime, that is the second derivative, which is 4 e to the 2x. What else? Plus 9, y prime, which is 2e to the 2x, minus 18 times y, which is the original function, e to the 2x. Hopefully this is equal to 0. What do you think? Is that equal to 0? Do we have a 0 equal to 0? It is, right? Because here, what do we have? So, 8 minus 8 and 9 times 2, which is 18, minus 18, yes. This is 0 equals to 0, which is indeed a solution to the differential equation. All right? Let's talk about part B. Y equals to cosine of 3x. Okay, let me find the three derivatives. Y prime equals to negative 3 sine 3x. Y double prime equals to negative 9 cosine 3x, and y triple prime that equals positive 27 sine 3x. All right? Okay, so let's put everything together. Their derivative, which is 27 sine 3x, minus 2 times the second derivative, which is negative 9 cosine 3x, plus 9 times y prime, which is negative 3 sine 3x, and minus 18 times the original function, which is cosine 3x. Hopefully that equals to 0. Let's combine everything together. Okay, in this case, makes it easier because we combine cosines with cosines and sines with sines. Okay, so 27 sine 3x and minus another 27 sine 3x, right? And what about negative? The negative is positive 18 cosines and then minus 18 of the same cosines. Oh, so it is a solution. It's kind of weird, isn't it, that this equation has a solution just as an exponential solution and just a trigonometric solution. That's kind of weird, okay? Well, we'll find out why is this true, okay? So, what about y equals sine 3x? So that is y prime equals to cosine 3x. I mean 3 cosine 3x. Y double prime equals to, what is that? Negative 9 sine 3x. And y triple prime, that is negative 27 cosine 3x. All right? Okay, so y triple prime, negative 27 cosine 3x minus 2 times the second derivative, which is negative 9 sine 3x, and then plus 9 times the first derivative, which is 3 cosine 3x minus 18 times the original function sine 3x. Do we have another 0 equals to 0? So the cosines, negative 27 plus 27 cosines cancel out. And negatives and negatives, 18 sines minus 18 sines cancel out. 0 equals to 0. So an exponential, a cosine, a sine individually, they are solutions for each case, right? They're a solution to these funky differential equations. All right, one more. Let's have a look at the right-hand side. I mean, not the right hand, on the next page. Whoa, what about this solution? This proposed solution: 4e to the 2x plus 5 sine of 3x plus 3 cosine 3x. All right, we're going to write quite a bit here. Okay, first derivative. Y prime equals to, 8e to the 2x plus 15 sine 3x minus 9 sine, cosine minus 9 sine 3x, all right? So that is the first derivative. What about the second derivative? Second derivative, that is, I'm going to write it down here, y double prime equals to 16 e to the 2x, and then minus 15 times 3, is that 45? Sine 3x, and then minus 27 cosine 3x. What about triple prime? Whoa, 16 times 2, is that 32? 32 e to the 2x, and then minus 45 times 3, is that 90, 135, all right? 135 cosine 3x, and 27 times 3, is that 81? And it minus because the derivative of cosine is negative, times the negative, it's positive 81 sine 3x. All right, so those are the three derivatives of what we think it is a solution. Well, we want to verify to be a solution, of course. All right, let's substitute all this madness into the differential equation. Okay, which is the third derivative, which is 32 e to the 2x minus 135 cosine 3x plus 81 sine 3x. That's only the third derivative term. What does the differential equation say? It says minus 2 times the second derivative, minus 2 times the second derivative, which is what? 16 e to the 2x minus 45 sine 3x minus 27. What is that? 27 cosine 3x. Okay? And then what's next in the differential equation? Plus 9, the first derivative. Plus 9 times the first derivative, 8 e to the 2x, plus 15 cosine 3x, minus 9 sine 3x. And finally, minus 18 times the original function, the proposed solution actually, y equals to 4 e to the 2x plus 5 sine 3x plus 3 cosine 3x. Hopefully all this madness, all this beast adds up to 0 on the left hand side. Alright, let's talk about the exponential ones. Okay, for the exponentials, what do we have? 32 minus 32 here, right? And then we have 9 times 8 is that 72. 18 times 4, that's also 72. So the exponentials go away. Oh boy, the sines and cosines. Okay, so that's negative 45. Wait. Negative 135. Okay, so what do we have here? 27 times 2, is that 54? So we have negative 135 cosines. 27 times 2, that's 54. And I'm going to bookkeep because I don't want to write the whole thing again, right? You guys see what am I doing here? Okay, perfect, great. All right, cosines, 15 times 9. Big number. Can anybody help me with the calculator? 15 times 9, what's that? So that's 100. What was that? 135. Yes, 135 positive. And 3 times 18, that's a negative 54. So yes, these all add up to 0 cosines. Great. Sines. 81 sines. 45 times 2, that's okay, let me do it up here. Okay, I'm gonna erase this anyway. You can rewind the video if you want to look. Okay, so sines, that's 81 cosines. 45 times 2 is that 90 cosines, and then 9 times 9 negative, that's negative 81. And how many sines? 18 times 5, that's negative 90, which indeed add up to 0, right? What does that mean? 0 equals to 0. But look at the different solutions. They all look different. Some of them with coefficients, some of them exponential, some of them sines, some of them cosines. Well, we don't have time to discuss why is this possible. We're going to do that in the next lecture.